Welcome to Still Science Lab. Tonight, we peel back the layers of fear and superstition to address a mystery that defines the very movement of life itself. We are diving deep into the heart of the unseen to answer the fundamental question: what is radiation really made of? For most of us, the word radiation carries a heavy, almost visceral weight. It conjures images of sirens, hazmat suits, and the eerie, artificial green glow of cinematic disasters. We have been conditioned to see it as a silent poison, a spectral byproduct of our most dangerous technologies. But as we step into the lab of the mind, we must shed these cultural shadows. To truly understand the universe, we have to recognize that radiation is not merely a hazard found in a nuclear reactor or a medical imaging room. It is the fundamental language of reality. It is the invisible messenger that allows the universe to be something other than a cold, static, and silent grave. At its most basic, stripped of all its terrifying connotations, radiation is simply energy on the move. It is energy that has decided to leave home and travel across the void. In our daily lives, we are accustomed to energy moving through stuff. We feel the heat of a stove moving through a metal pan via conduction. We feel the warmth of a room as air circulates via convection. But radiation is the rebel of the physical world. It is the only form of energy transfer that does not require a medium. It does not need a solid to cling to or a gas to ride upon. It can leap across the terrifying, absolute emptiness of the vacuum of space, traveling billions of miles without a single molecule to help it along the way. Without this ability, our existence would be impossible. The sun is a colossal engine of radiation, and if it could not broadcast its energy through the vacuum, the Earth would be a frozen rock, drifting in a darkness so profound that even the concept of a day would have no meaning. To understand what this messenger is made of, we have to look at its two primary forms, the wave and the particle. Imagine a lake at dawn. If you throw a stone into the water, a ripple moves outward. The water molecules themselves stay relatively in place, but the energy of the splash travels across the surface. This is one way radiation travels as an electromagnetic wave. It is a synchronized shiver in the electric and magnetic fields that permeate the cosmos. From the massive, rolling radio waves that are longer than a skyscraper to the frantic, microscopic vibrations of gamma rays, this spectrum of light is how the universe shares its information. When you sit by a campfire and feel the warmth on your face, you are being bombarded by infrared radiation. When you look at the blue sky, your eyes are catching a tiny sliver of this radiant messenger. But radiation can also be a more literal traveler. Sometimes, it isn't just a wave or a ripple, it is a hail of subatomic bullets. This is particle radiation. When an atom becomes unstable, when its internal architecture becomes too heavy or too energetic to hold itself together, it fragments. It spits out pieces of itself at incredible speeds. Protons, neutrons, and electrons are launched into the void like shrapnel from a microscopic explosion. These are not waves of energy. They are bits of matter that have been energized to the point where they behave like projectiles. Whether it is a wave or a particle, the common thread is the message they carry. They are all taking energy from a source and delivering it to a destination. If we were to suddenly remove radiation from the universe, the result would be a cosmic horror far greater than any nuclear meltdown. Imagine a universe where energy could not travel. Instantly, every star in the sky would vanish. Not because they stopped burning, but because the news of their fire could no longer reach us. The sun would become a silent, invisible ghost. The heat within your own body would have nowhere to go. It could not radiate away from your skin. Communication would cease, as radio waves, Wi-Fi, and cellular signals would simply drop out of existence. But more fundamentally, the very bonds of matter would begin to fail. Atoms communicate with each other through the exchange of radiant energy. Without the invisible messenger, the universe would become a disconnected collection of lonely, frozen particles. It would be a big freeze, of a different kind, a total breakdown of the cosmic conversation. We often fear radiation because it is invisible, but its invisibility is exactly what makes it so efficient. It permeates us. Right now, as you listen to this, you are being bathed in radiation. There are cosmic rays from exploding stars in distant galaxies passing through your body. There is the terrestrial radiation from the trace amounts of uranium and potassium in the soil beneath your feet. Even your own body is a source of radiation. The carbon and potassium in your bones are quietly decaying, sending out tiny, invisible messengers into the room around you. We are radiant beings, living in a radiant world. The fear comes from the ionizing end of the spectrum, the high-energy messengers that are strong enough to knock electrons out of place and break the delicate threads of our DNA. But to fear all radiation is like fearing all sound, because a deafening explosion can hurt your ears. The beauty of radiation lies in its role as the connective tissue of the cosmos. It is the bridge between the distant past and our present moment. When we point our telescopes at the sky and see the faint glow of a galaxy from 10 billion years ago, we are receiving an ancient message delivered by radiation. Those photons have been traveling through the dark for an eternity, carrying the news of a star's birth or death across the unimaginable expanse. Radiation is the reason we know anything about the universe beyond our own atmosphere. It is the light that brings us the image, the heat that brings us the life, and the signal that brings us the data. We must also reconsider the glowing green myth. In reality, most radiation has no color that the human eye can see. If we could see the world as it truly is in the full electromagnetic spectrum, the world would be an overwhelming riot of activity. You would see the glow of the Wi-Fi router filling the room. You would see the infrared heat signatures of the people around you. You would see the ultraviolet traces left on the flowers in a garden. The universe is not a dark, empty space. It is a brightly lit, bustling marketplace of energy where every atom is shouting its presence through radiation. As we redefine this concept, we start to see that what radiation is made of depends on the scale of our inquiry. At one level, it is made of photons, packets of pure energy that bridge the gap between wave and particle. At another level, it is made of the broken shards of atoms, the debris of nuclear instability. But at the deepest level, radiation is made of will, the inherent drive of the universe to move toward equilibrium. Energy does not like to be bunched up, it wants to spread out. It wants to go from where it is hot to where it is cold, from where it is crowded to where it is empty. Radiation is the mechanism of that spreading. It is the universe's way of trying to find balance. Tonight, as we begin this exploration, let go of the green barrels and the sirens. Think instead of the first light of dawn, the hum of a radio, the warmth of your own skin, and the ancient light of the stars. These are all the same thing. They are all the invisible messenger. They are the proof that we are not alone in the void. that we are connected to every other star and atom in existence through a ceaseless, radiant dialogue. Radiation is the breath of the cosmos, the shimmering vibration of the fields, and the high-speed transit of the subatomic. It is the heartbeat of a universe that refuses to be still. By understanding it, we are not just learning about danger, we are learning about the very pulse of reality. We are stepping out of the shadows of myth and into the light of the fundamental truth that energy, once born, never wants to stay in one place. It wants to travel. It wants to tell the rest of the universe that it exists, and that telling, that journey of energy across the silence, is what we call radiation. It is the most natural, necessary, and magnificent process in the natural world. I hope you're ready to look past the fear and see the wonder. Because once you understand the messenger, you begin to understand the message. And the message is that the universe is alive with energy, constantly moving, constantly sharing, and constantly reaching out across the dark. This is the beginning of our quest to understand the invisible forces that shape everything we see and everything we are. This is the heart of the wonder. This is Still Science Lab. Good night, and let the journey begin. To understand the true nature of radiation, we must first recognize that we are swimming in a sea of invisible light. Our human eyes are magnificent instruments, but they are also incredibly narrow filters. We perceive a world of vibrant colors, from the deep crimson of a sunset to the electric violet of a lightning strike, and we assume that this is the full picture of reality. In truth, what we call visible light is nothing more than a tiny, almost infinitesimal sliver of a much larger, grander structure known as the electromagnetic spectrum. If the entire range of electromagnetic radiation were a piano keyboard that stretched across the continent, the portion that our eyes could actually see would be less than the width of a single key. The rest of the keyboard is playing a vast, silent symphony that permeates every corner of the universe. And it is this tapestry of energy that constitutes the primary form of radiation in the cosmos. At its core, this tapestry is woven from two inseparable threads: electricity and magnetism. This is why we call it electromagnetic radiation. Imagine a pool of water where the surface is perfectly still. If you dip your finger in and move it up and down, ripples travel outward. In the vacuum of space, there is a fundamental field, the electromagnetic field, that behaves much like that water. When a charged particle, such as an electron, moves or vibrates, it plucks this field. This pluck creates an oscillating electric field, which in turn generates an oscillating magnetic field. These two fields support each other in a rhythmic, self-sustaining dance, leaping through the void at the ultimate speed limit of the universe, 186,000 miles per second. This is the messenger we discussed, and its language is defined by its wavelength, the distance between the peaks of those ripples. At the far, low-energy end of this cosmic tapestry, the ripples are massive, slow, and rolling. These are the radio waves. To call them microscopic would be a total misunderstanding of their scale. A single radio wave can be the size of a football field, a mountain, or even miles long. Because their wavelengths are so long, they have very little energy. They lack the kick required to disrupt the atoms of your body. They pass through walls, through trees, and through your flesh without leaving a trace. We have harnessed these giants to carry our songs, our news, and our data across the planet. but they have existed since the beginning of time. Long before the first radio tower was built, stars and galaxies were broadcasting these low-frequency hums into the dark, a testament to the fact that the universe has always been loud, even if we didn't have the ears to hear it. As we move up the spectrum, the ripples begin to tighten. We arrive at microwaves. These waves are measured in centimeters, roughly the scale of a honeybee. While we most commonly associate them with the convenience of heating a meal, their role in nature is far more profound. Microwaves are the size that perfectly matches the rotational frequency of water molecules. When these waves pass through food, they cause the water molecules to twist and jiggle frantically, creating the friction we perceive as heat. Beyond the kitchen, these waves are the carriers of the oldest light in the universe, the faint afterglow of the Big Bang itself. Every time you see static on an old television, a small percentage of that noise is actually caused by the universe's earliest radiation, a microwave message from the dawn of time. Continuing our climb, the ripples shrink further until they reach the scale of a human hair. This is the realm of infrared radiation. We cannot see it, but we feel it intimately. Every object that has a temperature, including you, is a source of infrared light. This is the heat that radiates from a warm pavement or the person sitting next to you. It is the invisible glow of the living world. If we had infrared eyes, the night would not be dark. The forest would be ablaze with the heat of the animals, and the rocks would shimmer with the stored energy of the day's sun. Infrared is the primary way that energy is exchanged between the earth and the sky, the silent regulator of our planet's climate. Then we hit a very specific, narrow threshold. The ripples become so small that they are measured in nanometers, billionths of a meter. For a tiny window of frequencies, the universe suddenly becomes visible. This is light. It is a peculiar coincidence of evolution that our eyes are tuned to this specific band. It is the band where the sun happens to emit its peak energy, and it is the band where water is most transparent. Because we evolved on a watery planet orbiting a yellow star, we are specialists in this tiny slice of the tapestry. To us, this sliver is everything. It is the green of the forest and the blue of the ocean. But we must remember that visible is a biological label, not a physical one. To the universe, there is nothing inherently special about visible light. It is just a bridge between the heat of infrared and the energy of ultraviolet. As we cross the threshold of the violet, the tapestry becomes more energetic and, from a biological standpoint, more dangerous. We enter the realm of ultraviolet radiation. Here, the waves are the size of large molecules. They carry enough energy to begin interacting with the very structure of matter. This is where radiation shifts from being a gentle messenger to a subatomic intruder. Ultraviolet light has enough punch to knock electrons out of their orbits in our skin cells, triggering chemical reactions that lead to tanning, burning, or even the distortion of our DNA. It is a reminder that the electromagnetic tapestry is not just a carrier of information, it is a carrier of power. Higher still, the shiver of the field becomes frantic. We arrive at X-rays. These waves are so small that they are the size of individual atoms. Because they are so tiny and so energetic, they do not see the world as we do. To an X-ray, the soft tissues of your body are mostly empty space, but the dense arrangement of atoms in your bones acts as a barrier. This allows them to ghost through your skin and reveal the internal architecture of your frame. In the heart of stars and around the edges of black holes, X-rays are the screams of matter being crushed and heated to millions of degrees. They are the heralds of high-energy catastrophe. Finally, at the extreme end of the spectrum, we find gamma rays. These are the shortest, most energetic waves possible. Their wavelengths are smaller than the nucleus of an atom. If radio waves are the slow, rolling waves of a calm ocean, gamma rays are the frantic, needle-like vibrations of a high-tension wire. They are born in the most violent events in the cosmos: supernovae, the birth of black holes, and the decay of radioactive nuclei. A single gamma-ray photon carries more energy than millions of visible light photons combined. They are the ultimate penetrators, capable of passing through feet of concrete or inches of lead. They represent the limit of what the electromagnetic field can endure before the very concept of a wave begins to blur. What is truly remarkable about this tapestry is its absolute continuity. There are no lines in nature that separate a radio wave from a microwave. These are human categories, labels we have placed on a seamless gradient of energy. The tapestry is one single, unbroken sheet. Every form of radiation we have discussed is exactly the same thing, an oscillation of the electromagnetic field. The only difference is the speed of the vibration. It is as if the universe is playing a single-stringed instrument, and by changing the tension and the frequency, it produces everything from the warmth of a candle to the data in your phone to the lethal energy of a cosmic explosion. This realization should shift our perspective on the world around us. We often feel that we are standing in a quiet room, but in reality, we are standing in the middle of a torrential downpour of invisible light. Every second, billions of radio waves, microwaves, and infrared pulses are passing through your body. The air is thick with the glow of the planet and the broadcasts of the stars. We are blind to 99% of the reality we inhabit. We are like people trying to understand a symphony while only being able to hear a single note. The electromagnetic tapestry is the primary way the universe connects itself. It is the medium through which the sun feeds the plants, the stars reveal their chemistry, and the galaxies announce their distance. Radiation is not an intruder in our world. It is the fabric of our world. When we talk about radiation being made of something, we are talking about these ripples in the field, these photons that act as both waves and particles, carrying energy across the silence. To understand this tapestry is to recognize that we are part of a much larger conversation. We are the observers of a tiny sliver of light, but we are the inhabitants of a universe that is shimmering with an invisible, radiant glory from end to end. Our eyes show us the surface, but the spectrum shows us the truth, that everything is connected, everything is moving, and everything is glowing in a language we are only just beginning to decode. The transition from waves to matter marks a profound shift in our understanding of how the universe distributes its energy. In our previous exploration, we looked at the electromagnetic tapestry, the shimmering shivers of fields that carry energy as pure light, from the rolling waves of radio to the needle-thin vibrations of gamma. But radiation has a second, more visceral personality. Sometimes, the messenger isn't a weightless ghost of energy. Sometimes, the messenger is a physical chunk of an atom, a piece of matter launched into the void with terrifying intent. To understand this, we must zoom in past the electron clouds and into the crowded, claustrophobic heart of the atom, the nucleus. This is where we encounter the alpha particle, the heavy-duty cannonball of the subatomic world, and the first of the great fragments that reveal the inherent instability of the largest structures in nature. To appreciate why an atom would suddenly decide to throw a piece of itself away, we have to understand the internal politics of the nucleus. Imagine a room packed with people. Half of them are protons, and they are all carrying a massive positive electric charge. According to the laws of electromagnetism, these protons should hate each other. Like charges repel, and the closer they are, the more violent that hatred becomes. Within the infinitesimal confines of the nucleus, that repulsive force is screamingly loud. The only reason the nucleus doesn't instantly explode is because of the strong nuclear force. This is the cosmic glue, a force so powerful it can overcome the electric push, but it has one fatal weakness. Its range is incredibly short. It only works if the particles are practically touching. As we move up the periodic table to the heavyweights, the uraniums, the radiums, the radon, the nucleus becomes overstuffed. It is like an overpacked suitcase where the zipper is beginning to strain. In these massive atoms, the nucleus is so large that the protons on one side can no longer feel the glue from the protons on the other side. The short-range strong force is losing its grip, while the long-range electromagnetic repulsion is still pushing with full strength. The atom becomes unstable. It enters a state of perpetual tension, a nuclear anxiety that can only be resolved by losing weight. When the pressure becomes too much, the nucleus executes a sudden, violent act of self-surgery. It spits out a specific, highly stable bundle of particles to reduce its energy and find a more comfortable state. This bundle is the alpha particle. An alpha particle is not a random shard. It is a very specific package consisting of 2 protons and 2 neutrons. If this configuration sounds familiar, it should. It is exactly the same as the nucleus of a helium atom. But while the helium in a birthday balloon is a gentle drifting gas, an alpha particle is that same nucleus stripped of its electrons and fired out of a heavy atom at speeds reaching 15 million meters per second. This is why we call it a cannonball. In the subatomic scale, where electrons are like buzzing flies and gamma rays are like weightless shadows, the alpha particle is a massive, lumbering giant. It is 8,000 times heavier than an electron. It carries a double positive charge, making it a highly attractive, or rather, highly disruptive force as it plows through space. Because of its massive size and significant charge, the alpha particle's journey through the world is a short, destructive one. It is the ultimate subatomic bully. As it moves through the air, its positive charge acts like a powerful magnet, ripping electrons away from every atom it passes. This is the process of ionization. The alpha particle doesn't just pass through matter, it tears it apart at the molecular level. However, because it is so big and so busy stealing electrons, it loses its energy very quickly. It is like a massive bowling ball trying to roll through a room filled with feathers. It has a lot of momentum, but every collision slows it down significantly. In the open air, an alpha particle can usually only travel an inch or 2 before it gets tired, grabs 2 stray electrons from the environment, and settles down to become a harmless, ordinary atom of helium. This brings us to a strange paradox regarding safety. If you were to hold a source of alpha radiation in your hand, perhaps a small piece of uranium ore, it would be largely harmless to you. The cannonball is so large that it cannot penetrate the dead layer of skin on the surface of your body. Your skin acts as a bulletproof vest against alpha particles. Even a single sheet of paper or a few centimeters of air is enough to stop them in their tracks. In the world of external hazards, alpha radiation is the least of our worries. It is a fragment of matter that is simply too thick to get inside us. But the story changes completely if the geography of the encounter shifts. The very qualities that make alpha radiation easy to block its mass and its intense ionizing power make it a nightmare if it finds its way inside the body. If you breathe in dust containing an alpha-emitting isotope, or if you ingest it in contaminated water, the protective barrier of your skin is gone. Now, those subatomic cannonballs are being fired directly into the soft, living tissues of your lungs, your stomach, or your blood. There is no dead layer of cells to protect the delicate structures of your DNA. Once inside, the alpha particle is a wrecking ball in a glass house. Because it is so ionizing, a single alpha particle can cause massive localized damage. As it plows through a cell, it doesn't just ping the DNA. It can shatter both strands of the double helix, creating a level of damage that the cell's repair mechanisms cannot handle. While a high-speed electron, beta radiation, might pass through a cell like a needle, leaving a tiny hole, an alpha particle passes through like a steamroller. This is why certain substances, like radon gas or polonium-210, are so notoriously dangerous. Radon, a naturally occurring gas that seeps from the ground in many parts of the world, is the leading cause of lung cancer among non-smokers. It isn't dangerous because it's a gas. It's dangerous because when you breathe it in, it decays inside your lungs, firing alpha cannonballs into your most vulnerable tissue. There is a certain irony in the life of an alpha particle. It begins its existence as a desperate attempt by a heavy atom to reach stability. By spitting out this fragment, a uranium atom transforms into thorium. It literally changes its identity to find peace. The alpha particle itself, after its brief and violent career of destruction, eventually finds its own peace. Once it slows down and captures its electrons, it becomes helium, the second lightest and most noble of all elements. The same particle that can shatter the genetic code of a living cell is the same particle that, once quieted, provides the lift for a child's balloon or the cooling for a quantum computer. This highlights the dual nature of radiation as both a creative and a destructive force. In the crust of the Earth, the constant fizzing of alpha decay is a major source of our planet's internal heat. The warmth of the Earth's core, which drives the movement of continents and the eruption of volcanoes, is fueled in large part by the energy released as these massive fragments are launched from unstable nuclei. We are standing on a giant, slow-burning nuclear furnace, kept warm by the very shrapnel we fear. As we look at the alpha particle, we see a bridge between the world of energy and the world of matter. It reminds us that radiation is not always a wave. Sometimes, it is the universe literally falling apart, one small chunk at a time. It teaches us that danger is a matter of perspective and position. A cannonball is harmless if it's sitting in a museum, but it's catastrophic if it's fired into your living room. The alpha particle is a fragment of the ancient past, a piece of a star that was forged in a supernova billions of years ago, finally reaching its breaking point and screaming its way into the present. It is matter in a hurry, a heavy messenger carrying the news that even the strongest glue has its limits, and that sometimes the only way to survive is to let a piece of yourself go. In the grand tapestry of radiation, the alpha particle is the heavy thread, the physical reminder that the subatomic world is not just a place of ghosts and shadows, but a place of real, tangible impact. Nature is a master of disguise and a relentless alchemist. While the alpha particle we explored previously was a desperate attempt by a heavy nucleus to lose weight by throwing out massive chunks of itself, there is another, more subtle kind of instability that haunts the subatomic world. This instability isn't about size or mass, it is about identity. In the heart of the atom, there exists a delicate, unspoken ratio between protons and neutrons. When this ratio is thrown out of balance, when a nucleus has one too many neutrons or one too many protons, it doesn't just throw a tantrum, it undergoes a fundamental transformation. This brings us to the realm of the high-speed fugitives, beta radiation. Here, we witness the strange spectacle of a particle changing its very soul to maintain the harmony of the universe, a process governed by the most mysterious and shyest of all cosmic powers, the weak nuclear force. To understand the birth of a beta particle, we have to look closely at the neutron. In our traditional view of the atom, we often treat the neutron as a quiet, stable, and neutral observer, a heavy anchor that helps the strong force glue hold the feisty protons together. But the neutron has a secret. Outside the protective embrace of a stable nucleus, a lone neutron is actually an unstable entity. It is like a clock with a ticking fuse. If you leave a neutron by itself, it will survive for only about 10 to 15 minutes before it spontaneously falls apart. Even inside a nucleus, if there are too many of them, the pressure of being a neutron becomes too much to bear. But nature cannot simply delete a neutron. It must follow the strict laws of conservation. Energy, momentum, and electric charge are the unbreakable bookkeeping rules of the cosmos. To solve its identity crisis, the neutron does something extraordinary. It commits a form of subatomic alchemy. It transforms into a proton. This moment of transformation is the work of the weak nuclear force. If the strong force is the glue and electromagnetism is the spark, the weak force is the shapeshifter. It is the only force in the universe capable of changing a particle's flavor, turning one fundamental building block into another. In a flash of weak force magic, the neutral neutron becomes a positively charged proton. But this creates a problem on the cosmic balance sheet. The universe started with a neutral charge, and now it suddenly has a new positive charge. To keep the scales balanced, the universe must instantaneously create a negative charge to cancel it out. And so, from the pure energy of the transformation, an electron is born. This is the beta particle. But this is not the slow, orbiting electron of the atomic shells that we are used to. This is a high-speed fugitive, birthed in a nuclear fire and kicked out of the atom at velocities that can reach 99% of the speed of light. It is a tiny, needle-like projectile, thousands of times lighter than the alpha cannonball, but carrying a kinetic energy that makes it a formidable traveler. Because it is so much smaller and faster than the alpha particle, it behaves differently as it moves through the world. If the alpha particle is a bowling ball plowing through a room of feathers, the beta particle is a sniper's bullet. It doesn't hit everything in its path, but it can penetrate much deeper. It can sail right through a sheet of paper that would stop an alpha particle dead. It can even travel through several millimeters of human tissue before it finally loses its steam. However, as physicists began to study this process in the early 20th century, they noticed something terrifying. The math didn't add up. When they measured the energy of the departing beta particle and compared it to the energy lost by the nucleus, there was a gap. Energy was disappearing. For a moment, scientists feared that one of the most fundamental laws of reality, the conservation of energy, was being violated. It was as if a bank account were leaking money with no paper trail. In 1930, Wolfgang Pauli proposed what he called a desperate remedy. He suggested that there must be a third, invisible particle born in the decay, a particle so light and so elusive that it could carry away the missing energy without ever being detected. He called it the neutrino, the little neutral one. The neutrino is the true ghost of the radiation family. It has almost no mass, it carries no electric charge, and it almost never interacts with normal matter. Every time a beta particle is born, a neutrino is born with it, screaming away into the void. To a neutrino, the entire Earth is as transparent as a pane of glass. Right now, trillions of neutrinos from the Sun and from distant radioactive decays are streaming through your body, through the floor, and through the entire planet without hitting a single atom. To stop a single neutrino, you would need a wall of lead several light years thick. This ghostly companion is the silent partner of beta radiation, the keeper of the universe's energy books, and a reminder that for every visible messenger in the cosmos, there is often an invisible one holding the secret to the truth. But the story of beta radiation has a mirror image, a twist that introduces us to the world of antimatter. Sometimes, a nucleus is unstable because it has too many protons rather than too many neutrons. In this case, the alchemy works in reverse. A proton transforms into a neutron. To balance the positive charge that has now vanished, the universe spits out a positron, a particle with the same mass as an electron but with a positive charge. This is beta plus radiation. It is the arrival of antimatter in our daily reality. When a positron meets an ordinary electron, they don't just bounce off each other. They annihilate in a flash of pure energy. This fugitive from the nucleus is so short-lived in our matter-filled world that it almost instantly vanishes, but we have learned to harness this annihilation in medical technologies like PET scans to peer inside the human brain. Because beta particles are smaller and faster than alpha particles, their impact on our biology is different. They are less ionizing, meaning they don't rip atoms apart with the same brute force as an alpha cannonball, but because they can penetrate deeper, they can reach the living layers of the skin or even internal organs. While a piece of clothing or a thin layer of aluminum is usually enough to stop a high-speed beta fugitive, they can cause beta burns if they stay on the skin for too long. They are the middle children of the radiation world, not as heavy as alpha, not as ghostly as gamma, but possessing a persistent, penetrating energy that makes them vital to the functioning of the universe. We see the footprint of beta radiation in the most unexpected places. It is the engine behind carbon-14 dating, the cosmic clock that allows us to peer back thousands of years and determine the age of ancient civilizations and long-dead organisms. Within every living thing, a tiny fraction of the carbon is unstable, constantly undergoing beta decay. When an organism dies, it stops taking in new carbon, and the beta fugitives begin to tick away the seconds of history. We are, in a very literal sense, timed by the transformation of neutrons. Beyond the laboratory, beta radiation is a testament to the dynamic nature of the cosmos. It tells us that matter is not a static, finished product. Even the eternal building blocks of the nucleus are in a state of potential transition. The universe is constantly re-editing itself, flipping bits from neutral to positive, from matter to antimatter, all to find a state of lower energy and greater stability. The weak nuclear force, though it only acts over distances smaller than a proton, is the quiet architect of this change. It is the force that allows the sun to burn, for without beta decay, the sun could not fuse hydrogen into helium and would go dark in an instant. As we watch these high-speed fugitives escape the nucleus, we are watching the universe's balancing act in real time. We see the birth of the electron, the flight of the neutrino, and the transformation of identity. The beta particle is a reminder that radiation is not just danger, it is the mechanism of change. It is the fugitive that carries the news of a nucleus reinventing itself. It is a sleek, fast, and energetic expression of the universe's refusal to stay still. In the grand tapestry of radiation, if alpha is the heavy, physical blow, beta is the subtle, transformative shift, the moment where the alchemists lead, finally, through the grace of the weak force, becomes gold. It is the high-speed story of how the universe keeps its books balanced, one ghostly neutrino at a time. After witnessing the physical debris of the atomic world, the heavy cannonballs of the alpha particle, and the high-speed snipers of the beta particle, we arrive at the most ethereal and haunting form of radiation. We have moved from the ejection of matter to the release of pure, unadulterated energy. This is the realm of the gamma ray, the penetrating ghost of the subatomic landscape. While its predecessors are physical travelers with mass and electric charge, the gamma ray is a phantom. It has no weight, it occupies no space, it carries no charge. It is, in its simplest essence, a photon on steroids, a pulse of light so energetic and so frantic that it exists at the absolute extreme of the electromagnetic spectrum. To understand gamma radiation is to understand how the universe sheds its final burdens of tension and how a nucleus, after the violence of transformation, finally finds its peace. To visualize why gamma radiation exists, we have to imagine the nucleus not as a static pile of balls, but as a vibrating, multi-layered structure of energy levels. When a nucleus undergoes alpha or beta decay, it is often left in what physicists call an excited state. Think of a person who has just survived a car crash. Even though the impact is over, their heart is racing, their adrenaline is surging, and their body is trembling with residual energy. The nucleus is much the same. It has just spat out a particle. It has changed its identity, and its internal arrangement is messy and chaotic. It is shaken up. To reach its stable, ground state, it must purge this leftover excitement. It doesn't do this by throwing out more matter. It does it by screaming. That scream is a gamma ray. Because a gamma ray is a photon, it is a wave of light. However, unlike the light that allows you to see the world, or the infrared that warms your skin, a gamma photon is packed with a terrifying amount of energy. If visible light is a gentle ripple on a pond, a gamma ray is a needle of energy vibrating with such intensity that it can pierce through almost anything. It is born from the most fundamental transitions within the heart of the atom, representing the vast difference between a nucleus that is uncomfortable and a nucleus that is at rest. Because it has no mass and no electric charge, it does not play by the same rules as the other forms of radiation we have discussed. This lack of charge is the secret to its ghostly nature. Alpha and beta particles are clumsy travelers. Because they are charged, they are constantly being pulled and pushed by the atoms they pass. They are like toddlers running through a crowded room, bumping into every person and piece of furniture until they lose all their momentum and stop. A gamma ray, however, is like a ghost walking through walls. It has no handles for other atoms to grab onto. It doesn't care about the electric fields of the electrons or the magnetic pull of the nucleus. It simply glides through the empty spaces within matter. This is why gamma radiation is famously difficult to stop. While a sheet of paper can stop an alpha particle and a thin layer of aluminum can halt a beta fugitive, a gamma ray sees these barriers as if they were made of mist. It can pass through the human body as if we weren't even there. It can sail through inches of solid steel and feet of heavy concrete. To truly block a gamma ray, you need a material that is so dense, so packed with heavy nuclei, that the ghost eventually has a head-on collision with something solid. This is why we use lead or depleted uranium for shielding. In these materials, the atoms are so crowded that even a ghost eventually runs out of luck and hits a wall. But even then, some gamma rays will find a way through. They are the ultimate penetrators, the silent observers of the material world. From a biological perspective, this makes gamma radiation a unique and formidable challenge. Because it can pass through us so easily, It doesn't cause the surface damage that alpha or beta particles might. It doesn't burn the skin or stay trapped in the lungs. Instead, it provides a whole-body dose. As it passes through you, it occasionally strikes an electron or a nucleus, acting like a subatomic billiard ball. These rare but high-energy collisions can shatter DNA, disrupt cellular machinery, and cause long-term damage deep within the organs. You don't feel it happening. There is no heat, no sound, and no sensation. It is a silent, internal bombardment. Yet, as with all things in physics, this destructive power has a mirror image of profound utility. Because gamma rays are so good at killing cells and so capable of passing through matter, they have become one of our most effective weapons in the fight against cancer. In a process called gamma knife surgery or radiotherapy, doctors use highly focused beams of gamma radiation to target a tumor deep within the brain or body. A single beam is weak enough to pass through healthy tissue without causing much harm, but where dozens of these beams intersect at the exact coordinates of the tumor, the energy becomes lethal. It is a form of surgery without a blade, using the penetrating ghost to destroy the enemy from the inside out. We also use this ghostly energy to sterilize medical equipment and preserve food, killing bacteria and viruses that are too small to be seen but too resilient to be stopped by traditional means. Beyond our earthly applications, gamma rays are the messengers of the most violent events in the history of the cosmos. When a massive star runs out of fuel and collapses into a black hole, it often releases a gamma ray burst. For a few seconds, this single event can outshine an entire galaxy, releasing more energy than our sun will emit in its entire 10 billion year lifetime. These bursts are the brightest electromagnetic events known to exist. If a gamma ray burst were to occur within a few thousand light years of Earth, it could strip away our atmosphere and sterilize the planet in an instant. Fortunately, these events are rare and usually occur in the distant reaches of the universe, serving as cosmic flares that tell us where the most extreme physics is taking place. The gamma ray is a reminder that the universe is not just made of stuff, it is made of information and energy. When a nucleus settles down and releases a gamma ray, it is announcing its stability to the rest of reality. It is shedding its history of violence and taking its place in the quiet order of the atomic world. The gamma ray is the final word in the conversation of nuclear decay. It is the signature of an atom that has finally found its balance. In the grand hierarchy of radiation, if the alpha particle is the body and the beta particle is the movement, the gamma ray is the spirit. It is the pure, weightless expression of the atom's inner life. It reminds us that there is a level of reality where mass is irrelevant and only frequency matters. It shows us that even the most solid-seeming objects, the lead shields, the steel vaults, the human frame, are mostly transparent to the right kind of light. We live in a world that is constantly being pierced by these high-energy ghosts. They come from the soil, from the walls of our buildings, and from the depths of the stars. They are a constant, invisible background music to our lives. To understand them is to lose our fear of the unseen and replace it with an appreciation for the extreme. The gamma ray is not a monster, it is a limit. It is the fastest, smallest shiver that the electromagnetic field can produce. It is the universe's way of saying that energy will always find a way to move, to escape, and to be heard. As we hold this image of the penetrating ghost in our minds, we begin to see the atom not as a simple object, but as a complex source of diverse signals. It throws cannonballs, it fires snipers, and it screams ghosts. Each one tells a different story about the stability of matter and the flow of energy. The gamma ray is the most profound of these stories because it represents the moment of ultimate resolution. It is the light that follows the storm, It is the energy that remains when everything else has been stripped away. In the silence of the subatomic world, the gamma ray is the voice that says, "It is finished." We are travelers in a sea of this ancient, high-energy light, woven into a reality that is far more transparent and far more energetic than we ever dared to imagine. To navigate the world of radiation is to constantly walk a line between the harmless and the lethal. Yet to the naked eye, there is no signpost indicating where the safety ends and the danger begins. We have spent our journey thus far identifying the various messengers, the waves of light, the heavy alpha cannonballs, the high-speed beta snipers, and the ghostly gamma rays. But now we must address the most critical question of all: why? Why is it that the radio waves carrying your favorite song can pass through your body for a lifetime without a hint of harm, while a brief, silent encounter with a gamma source can rewrite your biological future? The answer lies in a single, violent mechanical process known as ionization. This is the great divide of the subatomic world, the threshold where energy stops being merely a signal and starts becoming a crowbar. To understand ionization, we have to look at the atom not as a solid object, but as a finely balanced social contract. At the center is the nucleus, and swarming around it are the electrons. These electrons are held in their orbits by the electric pull of the protons. But they aren't just floating there, they are bound by a specific amount of energy. Think of an electron as a ball sitting in a shallow bowl. To get the ball out of the bowl, you have to give it a specific kick of energy. If you nudge the ball gently, it might wobble, but it stays in the bowl. If you hit it with a puff of air, it might vibrate, but it remains trapped. But if you strike that ball with enough force to overcome the depth of the bowl, it flies out. Ionization is that moment of escape. When radiation has enough energy to physically rip an electron away from an atom, it ionizes that atom. The once neutral atom, which had an equal number of protons and electrons, now has a missing piece. It becomes an ion, a particle with a net electric charge. This might seem like a small technical detail, but in the world of chemistry and biology, it is an act of war. Electrons are the glue that hold molecules together. They are the currency of every chemical bond in your body. When radiation rips an electron away, it is effectively snapping the structural supports of your very existence. This is why we draw a hard line between ionizing and non-ionizing radiation. Everything on the lower energy side of the electromagnetic spectrum, radio waves, microwaves, infrared, and even visible light, is non-ionizing. These messengers simply do not have the punch to eject an electron. A radio wave might be miles long, and you could be bombarded by trillions of them, but each individual wave is too weak to act as a crowbar. It is like trying to knock down a heavy brick wall by throwing a billion ping-pong balls at it. No matter how many balls you throw, no matter how intense the pile becomes, a ping-pong ball simply does not possess the mass or velocity to dislodge a brick. In this metaphor, the brick is the electron, and the wall is your DNA. This is the fundamental reason why technologies like Wi-Fi, 5G, and cell phone signals which exist in the radio and microwave frequencies cannot cause the kind of damage we associate with radiation. They are physically incapable of ionization. They can shake an atom, causing it to vibrate and create heat, which is how a microwave oven works, but they cannot break the chemical bonds of your cells. To suggest that a non-ionizing wave could cause cancer is to ignore the most basic law of quantum mechanics. Energy is delivered in discrete packets called photons. If a single photon doesn't have enough energy to break a bond, a trillion of them won't do it either. They just make things a little warmer. But once we cross the threshold into ultraviolet, X-rays, and gamma rays, the rules change. We have entered the territory of the subatomic crowbar. Now, Each individual photon carries enough energy to act like a bullet. When an X-ray strikes an atom in your lung, it doesn't just warm it, it blasts an electron out of orbit. This creates a cascade of chaos. The newly created ion is chemically angry. It wants its electron back, or it wants to bond with something else immediately. It becomes a free radical, a highly reactive marauder that begins tearing through neighboring molecules to find stability. The primary target of this localized violence is your DNA. Your genetic code is a long, delicate chain of atoms held together by shared electrons. When ionizing radiation strikes this chain, it can cause single-strand breaks, or, more dangerously, double-strand breaks. If an alpha particle that heavy, double positive cannonball plows through a DNA strand, it doesn't just nudge the atoms, it creates a scorched earth path of ionization. It rips hundreds of electrons away in a tiny fraction of a millimeter. The DNA doesn't just break, it is shattered. Your cells have incredible repair crews. They are constantly scanning your DNA for errors and gluing pieces back together. But ionizing radiation is like a vandal who doesn't just break a window, but burns down the entire blueprints of the house. If the repair crew puts the DNA back together incorrectly, a mutation is born. This mutation can be silent, or it can be the first step on the road to cancer, a cell that has lost its instructions on when to stop dividing. If the damage is too widespread, if a person is hit by a massive dose of ionizing radiation all at once, the repair crews are overwhelmed. Cells die en masse, tissues fail, and we see the horrific progression of acute radiation syndrome. This is the danger we fear, and it is entirely a product of the mechanics of ionization. We can think of the difference between ionizing and non-ionizing radiation as the difference between being hit by a gentle breeze and being hit by a needle. The breeze might move a lot of air and carry a lot of total energy, but it won't pierce your skin. The needle carries very little total energy, but all of that energy is concentrated into a single, sharp point. Ionizing radiation is that needle. It is concentrated, high-frequency energy that can penetrate the surface of our atomic stability and strike at the core. This is why the dose and the type of radiation matter so much. We are constantly exposed to low levels of ionizing radiation from the sun, UV rays, and the earth, radon gas. But our bodies are designed to handle occasional broken windows. The danger arises when the rate of vandalism exceeds the rate of repair. It is a game of probability. Every time an ionizing particle or wave passes through you, it is like a high-speed projectile flying through a crowded library. Most of the time, it passes through the empty space between the shelves. Sometimes, it hits a book and knocks a few pages loose. But every so often, it hits the main server, the DNA, and causes a crash. Understanding the mechanics of ionization allows us to replace blind fear with informed respect. We realize that we don't need to fear the radiation from our remote controls or our light bulbs, because they are part of the gentle, non-ionizing background of our lives. They are messengers that carry information, not crowbars that dismantle matter. Conversely, we gain a deeper appreciation for why we wear lead aprons at the dentist or why we monitor the sun's UV index. We are protecting the delicate electronic balance of our atoms from the high-energy intruders that want to steal their glue. The universe is a violent place, filled with these subatomic projectiles, yet life has found a way to thrive in the crossfire. We are walking masterpieces of quantum engineering, held together by the very electrons that radiation seeks to eject. By understanding the threshold of ionization, we see the boundary between the energy that sustains us and the energy that can unravel us. We recognize that we are built from a fragile stability, a harmony of charges that can be disrupted by a single, well-placed shiver in the field. In the grand scheme of the cosmos, ionization is the process that allows stars to forge elements and black holes to announce their presence. It is the engine of change, but for us, on this small, blue planet, ionization is the reason we must guard our blueprints. It is the physical proof that energy is not just something we use. It is something that can fundamentally alter what we are. As we move forward, we will see how this ionizing power isn't just a threat from the lab or the hospital, but a constant rain from the stars, a celestial bombardment that has been shaping the evolution of life since the very beginning. We are the survivors of an ionizing universe, a testament to the resilience of the chemical bond in the face of the subatomic crowbar. We often think of the atmosphere as a quiet blanket, a gentle layer of gas that keeps the warmth in and the cold of the void out. But if we could see the world through the eyes of a high-energy physicist, the sky would look less like a blanket and more like a battlefield. Beyond the blue horizon, in the deepest reaches of the interstellar dark, the universe is engaged in a constant, high-speed bombardment. This is the celestial rain, a relentless downpour of matter known as cosmic rays. Despite their name, these are not rays in the sense of light or waves. They are physical shards of atoms, mostly lone protons, the naked hearts of hydrogen traveling at velocities so close to the speed of light that the laws of physics begin to warp around them. They are the fastest, smallest, and most energetic travelers in existence, and they have been screaming through the silence of space for millions of years before finally slamming into the Earth. The origins of this rain are found in the most violent cataclysms the cosmos has to offer. While our sun does emit a solar wind of charged particles, the truly high-energy cosmic rays come from far beyond our solar system. They are born in the dying breaths of massive stars, the supernovae. When a star explodes, it creates a shock wave of such staggering power that it acts as a cosmic particle accelerator, a natural version of the Large Hadron Collider, but on a scale of trillions of miles. In these chaotic magnetic fields, a simple proton can be whipped up to speeds that defy imagination. Other cosmic rays are launched by the engines of active galactic nuclei, supermassive black holes at the center of distant galaxies that spit out jets of matter across the void. By the time these particles reach us, they carry more kinetic energy than a well-aimed tennis ball, all packed into a single, infinitesimal subatomic point. If you were to stand in the open vacuum of space, this celestial rain would be a lethal hazard. Because these particles are traveling at relativistic speeds, they don't just hit matter, they pierce it with the energy of a freight train. They are the ultimate form of ionizing radiation. They can pass through the hull of a spacecraft, through the visor of an astronaut's helmet, and directly through the cells of the human brain, leaving a trail of shattered molecules and ionized atoms in their wake. But we, on the surface of our blue marble, are rarely aware of this bombardment. We are protected by two magnificent layers of invisible armor: the magnetosphere and the atmosphere. The first line of defense is the Earth's magnetic field. Deep within the core of our planet, a churning ocean of molten iron creates a massive magnetic bubble that extends tens of thousands of miles into space. This is our magnetic shield. Because cosmic rays are charged particles, mostly positive protons, they are sensitive to magnetic forces. As they scream toward the Earth, they hit this invisible wall and are deflected. They are caught in a cosmic dance, spiraling along the magnetic field lines, diverted away from the equator, and funneled toward the north and south poles. This is the origin of the aurora borealis and the aurora australis. When you see those shimmering curtains of green and violet light, you are witnessing the visual debris of a cosmic war. You are seeing the waste heat of the celestial rain as it is successfully turned away by the planet's magnetic armor. However, the magnetic shield is not perfect. Some particles are too energetic to be fully deflected, and others find their way through the weak spots at the poles. This is where our second line of defense, the atmosphere, takes over. When a high-energy cosmic ray strikes the upper atmosphere, it doesn't just pass through. It hits a molecule of nitrogen or oxygen with such violence that the atom literally shatters. This creates a particle shower or an air shower. The primary cosmic ray is destroyed, but its energy is transformed into a cascading waterfall of secondary particles, pions, muons, electrons, and neutrons that rain down toward the surface. Primary cosmic rays, the original travelers from the stars, mostly protons. Secondary cosmic rays, the shrapnel created by collisions in the upper atmosphere. The muon rain. By the time the shower reaches the ground, most of it consists of muons, heavy versions of electrons that can pass through your body, buildings, and even deep into the Earth's crust without you ever feeling a thing. This constant interaction with the celestial rain has profound implications for life on Earth. Throughout the billions of years of our history, cosmic rays have been a primary driver of biological evolution. As these secondary particles zip through the DNA of living organisms, they occasionally cause useful errors mutations that allow for the variation and adaptation that drive the survival of the fittest. We are, in a very literal sense, the children of the star's debris. Without the gentle, filtered touch of this cosmic radiation, the engine of evolution might have moved at a much slower pace. But in our modern, high-tech world, this rain has a darker side. As our electronic components become smaller and more complex, they become more vulnerable to single-event upsets. A single cosmic ray muon passing through a microchip can flip a 0 to a 1 in a computer's memory. This is why airplanes, which fly higher in the atmosphere where the rain is thicker, require specialized radiation-hardened electronics. It is also why satellite designers must build massive redundancies into their systems. A stray particle from a black hole 5 billion light-years away can, in a fraction of a nanosecond, crash a server or disrupt a global positioning signal. We are living in a digital age that is constantly being poked by the ghosts of dead stars. To understand the cosmic ray is to realize that the Earth is not an island. We are an open system, constantly exchanging matter and energy with the furthest reaches of the galaxy. The celestial rain reminds us of the interconnectedness of all things. The proton currently passing through your thumb may have once been part of a star in the Andromeda galaxy. It may have been ejected during a supernova that happened before the Earth was even formed. It has spent eons crossing the lonely dark, only to be stopped by the thin veil of gas that surrounds our world. It is a reminder that we are not just residents of a country or a planet, we are residents of a high-energy cosmos. As we stand under the open sky, we should feel a sense of profound gratitude for the invisible forces that guard us. The magnetosphere and the atmosphere work in a perfect, silent harmony to filter a lethal cosmic wind into a harmless biological stimulant. We live in the sweet spot of the radiation spectrum, protected from the cannonballs of space while still receiving the light and warmth we need to survive. The celestial rain is the universe's way of touching us, a constant reminder that the empty space between the stars is actually a bustling highway of information and power. The study of these rays is a search for the extreme limits of nature. When we detect a particle with the energy of a "oh my god" particle, a single proton traveling so fast that it carries the energy of a bowling ball, we are forced to rethink what we know about the engines of the particle, universe, What kind of black hole can throw a pebble that hard? What kind of magnetic field can act as a slingshot for the subatomic? These are the questions that keep the fire of curiosity burning. We conclude this reflection by looking at ourselves. We are made of the same stuff as these cosmic travelers. We are built from the carbon and oxygen forged in the same supernovae that launched the celestial rain. When a cosmic ray hits the atmosphere, it is simply a case of one piece of the star stuff meeting another. The rain is not an intruder, it is a homecoming. It is the universe's ancient energy finally finding a place to rest, absorbed by the air, the soil, and the very cells of our bodies. We are the witnesses to this grand, invisible symphony, a masterpiece of cosmic engineering that ensures that even in the silence of the night, the universe is never truly still. In the popular imagination, radiation is a rare and exotic phenomenon, something that belongs in the controlled environments of power plants or the far reaches of deep space. We have traced its path from the high-speed fragments of the nucleus to the celestial rain falling from the stars. But now, we must turn the lens inward and look at the most intimate, constant, and universal form of radiation in existence. It is not a product of nuclear decay or cosmic explosions. It is a byproduct of existence itself. It is the silent, invisible glow that emanates from every object in the universe, from the coldest moon to the warmest heart. This is the realm of thermal radiation, the warmth of being. It is the revelation that to have a temperature, to be anything other than a frozen, absolute void, is to be a broadcast station for energy. To understand the warmth of being, we must first confront the concept of temperature. In our macroscopic world, we think of hot and cold as simple sensations, the way a cup of coffee feels against our hands or the bite of a winter wind. But at the atomic level, temperature is simply a measure of motion. It is a tally of the frantic, chaotic jigging and wiggling of atoms and molecules. In a hot object, the atoms are vibrating with violent intensity. In a cold object, they are sluggish and slow. There is a theoretical limit to this stillness called absolute zero, a point where all atomic motion ceases. But the universe abhors this stillness. In every corner of reality, atoms are moving, and because atoms are made of charged particles, protons and electrons, this motion has a profound consequence. When a charged particle vibrates, it creates a disturbance in the electromagnetic field. It plucks the fabric of reality, sending out a ripple of energy. This means that every single object in your room right now, the chair you are sitting on, the walls around you, the cold glass of water on your desk is currently glowing with light. This light is called thermal radiation, and for most of the objects in our daily lives, it takes the form of infrared radiation. We cannot see it because our eyes are tuned to a higher frequency, but we are constantly swimming in this invisible sea of heat. We are not just illuminated by the sun or the lamps in our homes, we are illuminated by the objects themselves. The relationship between an object's temperature and the light it emits is governed by a beautiful and precise law known as the blackbody curve. It is a fundamental rule of the universe that dictates the color of heat. At room temperature, the atoms of a chair are vibrating at a frequency that produces long, low-energy infrared waves. If you were to heat that chair to a few hundred degrees, the vibrations would speed up. The ripples would become tighter and more energetic. Eventually, the chair would begin to glow a dull, deep red till it has finally crossed the threshold from the invisible infrared into the visible spectrum. Heat it further, and it turns orange, then yellow, then a brilliant, searing white as it begins to emit all colors of the visible spectrum simultaneously. This is why a heating element on a stove glows red, and it is why the sun, with its surface temperature of thousands of degrees, shines with the blinding white-yellow light that sustains our world. But the most fascinating participant in this radiant dialogue is you. You are a biological engine, burning fuel and generating heat to maintain a stable internal temperature. Because you are warm, you are a radiant being. If we were to turn off all the lights and look at you through an infrared camera, you would not be dark. You would be a brilliant, shimmering beacon of light in a dim room. You are constantly shedding energy into your environment in the form of infrared photons. Every second, you are broadcasting your presence to the universe. This is not just a poetic metaphor, it is a physical necessity. If your body could not radiate heat away, you would quickly overheat and perish. Radiation is the cooling system of life. This radiant exchange is a constant, two-way conversation. As you sit in a room, you are radiating energy toward the walls, and the walls are radiating energy back toward you. If the walls are colder than your skin, you send out more energy than you receive, and you feel a chill. If the walls are warm, they bombard you with infrared photons, and you feel a warmth. We often think of feeling heat as a result of touching something or feeling the air move, but a significant portion of our comfort is determined by this invisible exchange of light. You are literally painting your surroundings with your thermal signature, and the world is painting you back. The implications of thermal radiation extend far beyond the comfort of a living room. It is the primary tool that astronomers use to map the hidden reaches of the cosmos. Space is filled with vast clouds of gas and dust that are too cold to emit visible light. To a traditional telescope, these regions look like empty black voids. But to an infrared telescope, these clouds glow with the warmth of being. We can see the heat of newborn stars buried deep inside their nurseries and the faint thermal signatures of planets orbiting distant suns. Even the most empty parts of space are filled with the cosmic microwave background, the ultimate thermal radiation, the cooled-down heat of the Big Bang itself, which permeates every cubic centimeter of the universe at a temperature of just a few degrees above absolute zero. Thermal radiation also reveals the profound interconnectedness of matter and energy. It shows us that there is no such thing as a truly passive object. A rock sitting in the desert is not just sitting there. It is absorbing the high-energy radiation of the sun and re-emitting it as low-energy infrared radiation. It is a transformer of energy. The Earth itself acts as a massive thermal radiator. It receives the shortwave light from the sun, which passes easily through the atmosphere, and then tries to radiate that energy back into space as long-wave infrared. Greenhouse gases like carbon dioxide and methane are visible to this infrared light. They act like a thermal blanket, catching those outbound photons and reflecting them back toward the surface. The entire climate of our planet is a delicate balance in the budget of thermal radiation. As we reflect on the warmth of being, we see that radiation is the great equalizer. It is the bridge between the animate and the inanimate. At the level of the infrared, there is no fundamental difference between the glow of a human hand and the glow of a warm stone. We are all participants in the same energetic flux. We are all contributors to the entropy of the universe, spreading our energy outward until it reaches the furthest edges of the dark. This realization brings a sense of quiet majesty to the mundane. Every breath you take, every beat of your heart, and every thought that crosses your mind generates a tiny amount of heat that eventually leaves your body as a pulse of light. That light travels through the air, through the windows, and out into the night sky. The warmth of being that you feel right now is, in a very real sense, your contribution to the illumination of the cosmos. You are a star in your own right, small and dim compared to the giants in the sky, but governed by the same laws and woven from the same radiant fabric. We live in a world that is far more luminous than we perceive. Beneath the colors of the rainbow lies a deeper, warmer spectrum that defines the physical state of all things. To understand thermal radiation is to recognize that we are never truly still and never truly dark. As long as we exist, as long as our atoms are dancing the jig of life, we are radiant. We are the messengers of our own warmth, casting our shadows and our light into a universe that is waiting to receive them. The warmth of being is the final proof that to exist is to be active, to be connected, and to be a source of light in a universe that, without the vibration of matter, would be nothing but an eternal, frozen silence. To truly understand what radiation is made of, we must finally leave behind the comfortable world of solid objects and things that we can touch. Throughout our journey, we have spoken of cannonballs, snipers, and ghosts. We have used these metaphors to describe the diverse ways energy moves through the void. But at the deepest level of reality, the metaphors of the macroscopic world begin to fail. We reach a layer of existence where there are no objects at all, only a vast, shimmering ocean of potential. This is the perspective of quantum field theory, and it reveals that radiation is not something that travels through the universe. It is a disturbance of the universe. To understand radiation from this vantage point is to see it as a ripple in the very fabric of reality, a temporary excitation in an invisible field that permeates every point in space and time. Imagine for a moment that the entire universe is filled with an infinite, invisible sheet of silk, stretched tight in every direction. This sheet is what physicists call a field. There isn't just one sheet. There is a sheet for every type of particle we know. There is an electron field, a quark field, and most importantly for our current mystery, an electromagnetic field. In its lowest energy state, this sheet is perfectly flat and still. This stillness is what we perceive as empty space. But space is never truly empty. It is merely dormant. When an atom undergoes a transition, when a nucleus settles down or an electron jumps from a high-energy orbit to a lower one, it is like someone plucking a string on that invisible sheet of silk. That pluck creates a vibration, a ripple that travels outward from the source. This ripple is what we have been calling radiation. In this field-centric view, the distinction between a wave and a particle begins to dissolve into a more profound unity. For centuries, scientists argued over whether light was a continuous wave, like sound in the air, or a stream of discrete bullets. The quantum field perspective provides the answer. It is both, and it is neither. The photon is not a little hard marble of light flying through space. Instead, it is a packet of energy, a localized vibration in the electromagnetic field. Think of it like a wave in the ocean that is squeezed into a small, tight pulse. It has a specific amount of energy, which makes it act like a particle when it hits something, but it moves and vibrates like a wave. The photon is the quantum of the field, the smallest possible ripple that the cosmic silk can sustain. This shift in perspective changes everything about how we visualize radiation moving from a star to our eyes. In our old way of thinking, we imagined a particle leaving the star, traveling across the nothingness of space, and arriving at our telescope. But in the field perspective, the nothingness is the very medium of the journey. The star doesn't throw a photon. It vibrates the electromagnetic field that is already present at the star's surface. That vibration then propagates across the field, which is already present in the vacuum of space, until it reaches the field that is already present inside your eye. Radiation is the music played upon the instrument of the universe. The messenger is the vibration itself, moving through a medium that never moves, just as a wave moves through water without the water molecules themselves traveling to the shore. This field perspective applies not just to light, but to all forms of radiation. When we discussed beta radiation, the high-speed electrons fleeing the nucleus, we were actually seeing a ripple in the electron field. When we looked at the alpha cannonballs, we were seeing a complex excitation in the matter fields. Everything we perceive as a particle is simply a localized knot of energy in its respective field. The reason radiation can be so diverse, from the miles-long radio wave to the needle-sharp gamma ray, is simply because the electromagnetic field can vibrate at an infinite variety of frequencies. A radio wave is a long, slow, gentle undulation of the field, like the deep swell of the open ocean. A gamma ray is a frantic, high-energy shiver, like the vibration of a hummingbird's wing. They are the same fabric, just different rhythms. This leads us to one of the most mind-bending realizations of modern physics. The vacuum is not empty. Even in the deepest, darkest void between galaxies, the fields are still there. And because of the laws of quantum mechanics, these fields can never be perfectly, absolutely still. They are always jittering with a tiny amount of energy known as vacuum fluctuations. This means that space itself is a boiling cauldron of potential radiation. Every so often, two ripples can spontaneously appear out of the field, exist for a billionth of a second, and then vanish back into the stillness. We call these virtual particles. Radiation, in this sense, is just the visible part of a much deeper, hidden sea of energy. What we call a photon is simply a ripple that has enough energy to become real and travel across the cosmos. When we consider the danger of ionizing radiation through this lens, we see it as a mismatch of frequencies. Your body is also a collection of fields, electron fields and quark fields organized into stable, beautiful patterns. When a low-frequency radio ripple passes through you, its rhythm is too slow to disturb the stable knots of your atoms. It passes through like a low bass note through a wall. But a gamma ray or an X-ray is a high-frequency vibration that matches the internal tuning of your atomic bonds. It jiggles the field so violently that the knot of the electron is shaken loose from the knot of the nucleus. Ionization is a resonance catastrophe, a moment where the rhythm of the incoming radiation shatters the rhythmic stability of the atom. The quantum field perspective also explains why radiation doesn't need a medium like air or water to travel. In the 19th century, scientists were obsessed with finding the aether, the mysterious substance that carried light waves. They couldn't imagine a wave without a medium. But the field is the medium. It is a fundamental property of space itself. You cannot have space without the electromagnetic field, just as you cannot have a trampoline without the fabric. This means that radiation is the most at home in the vacuum. It is the purest expression of the universe's geometric and energetic potential. By seeing radiation as a disturbance in the fabric, we move away from the idea of scary particles hitting us and toward the idea of a universe that is fundamentally musical. Every atom in your body is a set of standing waves in these fields, and every bit of radiation you encounter is a traveling wave. We are not separate from the radiation. We are made of the same fields, just vibrating in a different way. We are the stable, complex chords in a symphony where radiation is the melody. This perspective grants us a profound sense of unity. When you look at the light from a distant star, you are literally touching a field that stretches from that star all the way to your retina. There is no gap between you and the star. There is only the field and the ripple moving through it. The invisible messenger is not a traveler from a distant land. It is a pulse moving through the very ground you stand on. It is the universe talking to itself through the vibrations of its own skin. As we reach the limits of our understanding, the quantum field perspective invites us to see the world with a sense of transparency. The walls, the floor, the stars, and your own body are all just different ways that the underlying fields are excited. Radiation is the evidence of this underlying reality. It is the shimmer that reveals the existence of the hidden fields. It is the proof that even in the darkest, most empty corners of the universe, something is there, waiting to be plucked into life. We are not living in a world of things. We are living in a world of vibrations, a cosmic tapestry where every ripple, no matter how small, carries a piece of the story of the whole. To understand radiation as a field is to realize that the universe is not a collection of parts, but a single, continuous, and infinitely vibrant whole. Our journey through the unseen world has brought us from the visceral impact of subatomic cannonballs to the shimmering abstractions of quantum fields. We have seen how radiation is not a singular, terrifying entity, but a vast and varied spectrum of messengers, each carrying its own unique story about the state of matter and the flow of energy. We have learned that we are not merely passive observers of this radiant world, but active participants, beings of light and heat who are constantly broadcasting our own thermal signatures into the dark. But as we stand at the end of our inquiry, we must zoom out even further, beyond the scale of atoms and stars, to listen for the oldest and most profound sound in the cosmic symphony. We must listen to the eternal echo that defines the very boundaries of our reality, the cosmic microwave background radiation. For most of this exploration, we have focused on radiation that has a clear, localized source, a decaying nucleus, a vibrating electron, or a dying star. But if you were to take a sensitive enough antenna and point it at the empty patches of sky between the galaxies, you would find that the darkness is not truly black. It is filled with a faint, persistent hum of energy. This is the afterglow of the Big Bang itself. About 380,000 years after the beginning of time, the universe had cooled enough for the first atoms to form. Before that moment, the cosmos was a hot, dense plasma, a thick fog where light could not travel because it was constantly being scattered by free electrons. But as the fog cleared, the first photons were finally set free. They began a journey across the expanding void that has lasted for nearly 14 billion years. As the universe expanded, these ancient messengers were stretched. What began as high-energy, searing light has been drawn out into long, low-energy microwaves. This radiation is the oldest thing we can ever hope to see. It is a baby picture of the cosmos, a snapshot of the moment when the universe first became transparent. It is the ultimate proof that radiation is not just a byproduct of the universe. It is the primary record of its history. Every cubic centimeter of space, including the space inside your own body right now, contains hundreds of these ancient photons. You are literally inhabited by the light of creation. This eternal echo is the foundation upon which everything else, every star, every planet, and every living cell has been built. Reflecting on this ancient light allows us to see radiation in its true philosophical context. Throughout these 10 chapters, we have dismantled the glowing green stereotype and replaced it with something far more majestic. Radiation is the language of the stars. It is the only way the distant suns can tell us what they are made of, how hot they are, and how fast they are moving. Without the letter delivered by the photon or the shrapnel of the cosmic ray, we would be trapped in an eternal, ignorant isolation. We would know nothing of the furnace of the sun or the mystery of the black hole. Radiation is the carrier of information. the bridge that allows the human mind to reach out and touch the furthest edges of the observable universe. But it is also more than just a signal. It is the very breath of a living, energetic cosmos. We live in a universe that is fundamentally restless. From the frantic jiggling of thermal heat to the violent transitions of the nucleus, energy is always seeking to move, to spread, and to transform. Radiation is the mechanism of that restlessness. It is the way the universe breathes out its excess energy so that it can find a new state of balance. If the universe were perfectly still, it would be dead. If it were perfectly contained, it would be a silent tomb. Radiation is the proof of life. It is the evidence that the cosmos is a dynamic, evolving masterpiece that is constantly sharing its wealth of energy across the silence. We must also confront the paradox of our own existence in this radiant sea. We are fragile beings, built from delicate chemical bonds that can be shattered by a single high-energy gamma ray. And yet, we are also the products of this energy. We are fueled by the radiation of the sun, timed by the beta decay of carbon, and evolved by the gentle touch of cosmic rays. The very forces that can unravel us are the forces that created us. This is the dual nature of the universe. It is both a furnace and a garden. We survive by living in the sweet spot of this spectrum, sheltered by our magnetic fields and our atmosphere, like travelers sitting near a campfire close enough to feel the warmth, but far enough to avoid the flames. To understand radiation is to lose the primitive fear of the invisible. We realize that the unseen is not synonymous with the hostile. Most of the radiation in your life is the gentle hum of the world talking to itself. It is the infrared glow of your home, the radio waves carrying the world's knowledge, and the visible light that reveals the beauty of a flower. Even the ionizing messengers, the ones we must treat with respect and caution, are simply part of the natural order of a universe that is made of heavy, complex elements. They are the price we pay for living in a world that is rich enough and complex enough to support consciousness. As we conclude this series, I hope you carry away a new sense of vision. When you look at the night sky, I hope you don't just see points of light, but a torrential downpour of information and power. I hope you see the celestial rain falling silently through the atmosphere. When you feel the sun on your face, I hope you remember the invisible messenger that leaped across 93 million miles of vacuum to touch you. And when you look in the mirror, I hope you see yourself as a radiant being, a localized storm in the electromagnetic field, glowing with the warmth of being, contributing your own tiny, unique vibration to the eternal symphony of the cosmos. We are not separate from this radiant reality. We are the place where the radiation of the universe finally becomes aware of itself. We are the eyes that catch the photon and the minds that decode the message. The story of radiation is the story of our own origins, our own survival, and our own connection to the infinite. It is a story that began with a flash of light 14 billion years ago and continues in every beat of your heart and every signal in your brain. The search for the core of the electron, the hunt for the fragments of the nucleus, and the observation of the cosmic afterglow are all parts of the same great human endeavor. To understand the fabric of the home we inhabit, we have found that the universe is deeper, more energetic, and more interconnected than we ever could have imagined. It is a place where nothingness is full of potential, where solid is an illusion of fields, and where the most important forces are the ones we cannot see. As we dim the lights in the lab tonight, remember that the silence is never truly silent, and the darkness is never truly dark. The fields are always vibrating, the messengers are always traveling, and the eternal echo of our beginning is still ringing out, carrying the news of our birth to the furthest reaches of the future. We are travelers in a sea of light, and the journey of discovery never truly ends. It only changes frequency. Thank you for joining me on this exploration of the invisible. It has been an honor to walk these subatomic paths with you and to listen to the whispers of the universe's most profound messengers. Keep your curiosity bright, for it is the most powerful radiation of all the light that reveals the truth behind the shadows. Good night, fellow travelers. Sleep well in the warmth of this radiant cosmos. I look forward to our next journey into the heart of the wonder. I will see you in the next video.